Our universe is hiding secrets that defy the laws of physics as we know them. For centuries, we have trusted certain rules to explain the cosmos, but a collection of strange cosmic anomalies is forcing scientists to reconsider everything. Albert Einstein called the mysterious the most beautiful thing we can experience, and these 20 cosmic puzzles live up to that wonder. We will journey from unexplained gravitational waves to bizarre celestial objects that simply should not exist. By the end of our exploration, you will see the universe not as a finished map, but as a living frontier of endless questions. What if empty space itself holds an immense, hidden energy? Why do some stars wink out in ways that no known object can explain? This is your guide to the phenomena that could completely redefine reality. What do you believe is waiting to be discovered in the dark? Two spacecraft, Pioneer 10 and Pioneer 11, sailed through the void for decades as testaments to human ingenuity. Yet, as they journeyed farther from the sun, a ghost began to tug at them. It was not a dramatic pull, but a whisper, a tiny, unrelenting deceleration that defied every calculation. Mission controllers found their trajectories ever so slightly off course, as if an invisible hand was gently applying the brakes. This was the Pioneer Anomaly, a persistent drift that refused to be explained by the gravity of the sun or its planets. The force acting on the probes was minuscule, comparable to the weight of a single grain of sand pressing on your hand, but over millions of miles, that tiny push added up to a monumental mystery. Physicist John Anderson called it a ghost in the machine of orbital mechanics, a phantom force that seemed to rewrite the rules of the solar system. Scientists meticulously checked every possible conventional cause. Could it be the faint pressure of heat radiating from the spacecraft's own power source? They modeled the thermal radiation. Could it be a tiny, undetected fuel leak? They calculated and recalculated. Each time the numbers fell short, the anomaly remained stubborn and real. This left a tantalizing possibility that we were seeing the first hints of new physics. Some theorists proposed modifications to our fundamental understanding of gravity itself, a concept known as modified Newtonian dynamics. Others wondered if the faint tug was a local effect of dark energy, the very force driving cosmic expansion, acting in our own celestial backyard. The mystery only deepened with data from other missions. The Voyager probes, built with a different design, did not experience the same pronounced effect. The Cassini spacecraft orbiting Saturn showed no such anomaly. This suggested the ghost was not universal, but perhaps something unique to the Pioneer's path or construction, an environmental clue we have yet to fully decipher. What if this subtle, almost imperceptible drag is a signal from a hidden layer of reality, a cosmic force we are only just beginning to sense? It is a reminder that even in the emptiness of space, the universe holds onto its secrets tightly. That ghostly tug on the Pioneer probes hints at forces we cannot see, but there is another, far more massive presence warping the cosmos around us. Light itself bends around colossal galaxy clusters, creating cosmic mirages that reveal an invisible architecture. The amount of bending is so extreme that it implies the presence of a tremendous amount of mass, a gravitational anchor that we simply cannot see with any telescope. This is the domain of dark matter, an entity that does not emit, absorb, or reflect light, yet whose gravitational pull is the dominant force sculpting the universe on the largest scales. The evidence for this shadowy component began closer to home with the pioneering work of astronomer Vera Rubin. She meticulously charted the rotation of stars within spiral galaxies, finding a profound puzzle. The stars at the outer edges of galaxies were moving just as fast as those near the center, a behavior that defied the laws of gravity as we knew them. According to Newton and Einstein, these distant stars should have been slowing down, flung away by their own speed, unless an immense amount of unseen matter was holding them in a gravitational grip. The visible stars and gas were simply not enough. This was the first strong hint of a dark, massive halo enveloping every galaxy. We can now witness this invisible hand at work through the phenomenon of gravitational lensing. Think of space-time as a vast, flexible sheet. A massive object like a galaxy cluster creates a deep depression in this sheet. When light from a more distant galaxy travels toward us, its path bends as it passes through this warped region, much like a lens of glass bends light. Astronomers observe this as stretched and distorted arcs of light, or sometimes as multiple, identical images of the same background galaxy. The degree of this bending allows scientists to literally weigh the cluster. Time and again, the gravitational mass calculated from the lensing effect is many times greater than all the visible matter combined. This discrepancy is the fingerprint of dark matter. One of the most dramatic confirmations of this came from observations of the Bullet Cluster, a spectacular collision of two galaxy clusters. During the collision, the hot gas of normal matter, which is visible in X-rays, slammed into itself and slowed down. Meanwhile, the dark matter, which does not interact with anything but gravity, sailed right through the collision. The result was a clean separation. The majority of the mass mapped through its gravitational lensing effect was located in a different place than the normal matter we could see. It was a direct visual proof that most of the universe's matter is something entirely other. Telescopes like Hubble use both strong and weak lensing to map this hidden cosmic scaffold. Strong lensing creates those dramatic, banana-shaped arcs and Einstein rings around the densest clusters. Weak lensing, a far more subtle effect, causes tiny, systematic distortions in the shapes of millions of background galaxies, allowing scientists to create vast three-dimensional maps of the dark matter web that spans the universe. Projects like the Dark Energy Survey use this technique to chart the distribution of this invisible mass on a grand scale. So, what is this stuff? We do not know. It could be a sea of exotic particles that barely interact with normal matter, or it could be a sign that our understanding of gravity is fundamentally flawed on cosmic scales. How might understanding this invisible scaffold, the very skeleton of the cosmos, revolutionize our view of everything from the birth of galaxies to the ultimate fate of the universe? This mysterious substance is the foundation upon which the visible universe is built, yet it points toward an even more enigmatic and powerful force lurking in the void. If the dark matter scaffolding holds galaxies together, then dark energy is the force tearing the cosmic fabric apart on the grandest scale. The universe is not merely expanding, it is accelerating, with galaxies fleeing from one another at a pace that grows faster with every passing moment. This monumental discovery came from two independent teams in the late 1990s who were using distant stellar explosions to measure the expansion history of the cosmos. They studied a specific kind of supernova known as Type 1a. These cosmic blasts occur when a white dwarf star steals too much mass from a companion and crosses a critical threshold, triggering a detonation so uniform that its peak brightness is almost always the same. This makes them perfect standard candles, allowing astronomers to gauge their true distance with remarkable precision. By comparing this distance to the speed at which the supernova's host galaxy is moving away, the teams expected to measure how much the universe's expansion was slowing down over time due to the collective gravity of all matter. Instead, they found the opposite. the most distant supernovas were fainter than they should have been, meaning they were farther away than anyone predicted. The expansion of the universe was not slowing, it was speeding up. This shocking result, which earned its discoverers the Nobel Prize, pointed to a mysterious repulsive force counteracting gravity. Astrophysicist Saul Perlmutter, a leader of one of the teams, described it as a universe that had its foot on the accelerator. This force was dubbed dark energy. The evidence for its dominance only grew stronger. Data from the Planck satellite, which mapped the faint afterglow of the Big Bang known as the cosmic microwave background, revealed the precise recipe of the universe. It confirmed that dark energy constitutes about 68% of the cosmos, while dark matter makes up another 27%. The normal matter, everything we can see and touch from stars to planets, accounts for a mere 5% of the total. The nature of this dark energy is one of physics' greatest puzzles. The simplest explanation is Einstein's cosmological constant, a kind of innate energy woven into the fabric of empty space itself. This energy has a negative pressure, causing it to push and drive the acceleration. But its observed value is staggeringly small compared to what quantum theory predicts, creating a discrepancy of 120 orders of magnitude, the worst theoretical mismatch in the history of science. Other theories suggest dark energy is not a constant, but a dynamic field that evolves over time, an idea sometimes called quintessence. The equation of state for dark energy, a single number describing its pressure and density, is the key to unlocking its identity. If this value is exactly -1, it points to a cosmological constant and a universe destined for a slow, cold big freeze, where galaxies drift apart into eternal isolation. If the value is less than -1, it could lead to a catastrophic big rip, where the accelerating expansion becomes so violent that it tears apart galaxies, stars, planets, and eventually the very atoms of matter itself, billions of years from now. Projects like the Dark Energy Survey are mapping the distribution of millions of galaxies to trace how the influence of dark energy has changed over cosmic history. The upcoming James Webb Space Telescope will peer back to the universe's youth to see how the first structures formed under the competing influences of gravity and dark energy. Could this inexplicable acceleration be a sign of new physics beyond Einstein's relativity, a flaw in our understanding of space and time on the largest scales? As this force reshapes the cosmos, it presents another profound mystery, one that arises not from the vast emptiness, but from the fundamental laws that govern the smallest particles. While dark energy stretches the cosmos on a grand scale, the universe also crackles with brief, violent flashes that arrive without warning. These are fast radio bursts, sudden blasts of radio waves so powerful they can outshine entire galaxies for a few thousandths of a second. Each burst releases as much energy as our sun emits over many days, all compressed into a blink of an eye. They travel across billions of light years, arriving at our telescopes as a ghostly signal that vanishes almost as soon as it appears. The first was spotted in archived data from 2007 by astronomer Duncan Lorimer, a spike so intense and so brief it seemed almost impossible. For years, it was a singular mystery, a one-off event that defied all explanation. Then, scientists found another, and eventually one that did something extraordinary. It repeated. Known as FRB 1211-2, this repeating burst confirmed these were not just final, catastrophic explosions, but that some sources could flare again and again, ruling out events that completely destroyed their origin point. The extreme unpredictability and sheer power of these bursts challenge everything we know about high-energy physics. What kind of cosmic engine can produce such a staggering amount of energy in such an impossibly short time, and then, in some cases, do it over and over? To solve this, astronomers have raced to pinpoint the home galaxies of these bursts, using vast radio telescopes like the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, which scans the entire northern sky every day. Scientists have begun to localize these events. The results are deeply puzzling. Some fast radio bursts originate in the chaotic, star-forming regions of distant galaxies, where young, massive stars live fast and die young. This points to origins like magnetars, which are neutron stars with the most powerful magnetic fields in the universe. A starquake on a magnetar's incredibly dense crust could, in theory, unleash a firestorm of radio waves. Yet other bursts have been traced back to much quieter, more elderly galaxies, environments where such young, violent stars should not exist. This suggests multiple, completely different origins for what appears to be the same phenomenon. The list of proposed mechanisms reads like a catalogue of cosmic catastrophes. Could they be the product of two ultra-dense neutron stars spiraling into each other and merging in a final, brilliant flash? Some theorists have even suggested they are the result of cosmic strings, hypothetical defects in the fabric of space-time itself, vibrating and releasing immense energy. Others ponder if they are signs of new, exotic particle interactions. Each new burst that is caught provides a clue. One particularly telling case was FRB 2021-124a. Analysis of its light revealed complex and rapidly changing polarization, a sign that the magnetic environment around the source is incredibly turbulent and dynamic. This strongly supports the idea of a magnetar lurking in a complex nebula of its own making, a cosmic dragon in its lair. So what are these cosmic sirens telling us? They are likely not messages from other civilizations, but something perhaps even more profound. They are natural laboratories, testing matter under conditions of density and magnetic field strength so extreme they are impossible to recreate on Earth. Each millisecond flash is a message from the most violent neighborhoods in the universe, a brief window into physics at its absolute limit. The mystery of their power connects to an even deeper puzzle, one that strikes at the heart of our most fundamental theories of reality. The violent unpredictability of fast radio bursts reveals a universe of extremes, but a quieter, more persistent anomaly is challenging our understanding of the cosmos on its most fundamental scale. Two different ways of measuring the universe's expansion rate, both incredibly precise, are yielding two different answers. This is the Hubble tension, a crisis in cosmology that suggests our standard model of the universe may be profoundly incomplete. One method looks back to the dawn of time, studying the faint afterglow of the Big Bang known as the cosmic microwave background. Satellites like Planck have mapped this primordial light in exquisite detail, allowing scientists to calculate how fast the universe must have been expanding in its infancy to produce the structures we see today. This early universe measurement gives us one very specific value for the Hubble constant, the number that describes the current expansion rate. The other method uses a cosmic ladder of distance markers within our local universe. Astronomers observe pulsating stars called Cepheid variables, whose intrinsic brightness is tied to their pulse period. By measuring their apparent brightness in nearby galaxies, they can determine precise distances. Combining this with measurements of how fast those galaxies are moving away from us gives a second, independent value for the Hubble constant. The problem is stark: these two numbers do not agree. The local measurements, like those from the SH0ES project using the Hubble Space Telescope, suggest a faster expansion rate than the predictions based on the early universe. The uncertainties in both methods are now so small that the chance this is a simple statistical fluke is vanishingly slim. Leading cosmologist Wendy Friedman has been at the forefront of this work, and her teams have consistently found that this tension persists even when using different cosmic markers, like ancient red giant stars, to cross-check the Cepheids. It refuses to go away. This is not a small rounding error. It is a direct conflict between two pillars of modern science. What if the universe today is expanding faster than our best models, based on its initial conditions, say it should be? This discrepancy forces physicists to consider extraordinary possibilities. Perhaps there was a burst of unknown energy in the universe's first moments, an early dark energy that subtly changed the expansion history. Maybe neutrinos, the ghostly particles that stream through everything, have exotic properties we have not yet detected. Some even speculate that dark energy itself is not constant but has evolved in an unexpected way. To break the deadlock, scientists are turning to entirely independent probes. The detection of gravitational waves from colliding neutron stars provides a new way to measure cosmic distances without relying on stars. Future missions like the Nancy Grace Roman Space Telescope are designed to scan vast volumes of space, mapping the distribution of galaxies and the behavior of supernovas with unprecedented precision to pinpoint the source of the discrepancy. Is this a flaw in our measurements, or is it a gateway to undiscovered cosmic ingredients? The Hubble tension reminds us that our map of the cosmos is still being drawn, and the next line we trace might lead to a revolution. This fundamental uncertainty about the very fabric of expansion finds a strange parallel in the behavior of the smallest particles, where the rules of reality seem to bend in ways that defy common sense. That fundamental uncertainty about the cosmos finds a strange echo in the very first light of the universe, a signal that seems to single us out in a way that should be impossible. The cosmic microwave background, the afterglow of the Big Bang, is supposed to be the most uniform thing we can observe. According to the bedrock cosmological principle, the universe should look the same in every direction, with no center and no special place. Yet, when scientists created a full sky map of this ancient radiation, they found a puzzling alignment, a so-called axis of evil. This axis is a mysterious preferred direction in space, a line along which the largest temperature fluctuations in the cosmic microwave background appear to be strangely correlated. Even more unsettling, this axis aligns suspiciously well with the plane of our own solar system. It is as if the universe's grandest blueprint has a faint arrow pointing directly at us, a notion that profoundly challenges the principle that we do not occupy a privileged location. Physicist Kate Land has called this alignment an embarrassment for the standard model of cosmology, because it simply should not be there. The discovery came into sharp focus with data from the Wilkinson Microwave Anisotropy Probe, or WMAP, and was later confirmed with even greater precision by the European Space Agency's Planck satellite. These missions mapped the tiny temperature variations in the cosmic microwave background, the seeds from which all galaxies would eventually grow. Scientists analyzed these variations using a mathematical technique that breaks down the map into components called multipoles. The simplest components, the quadrupole and octupole, which represent the very largest patterns on the sky, show this strange coherence. Instead of being randomly oriented, their hot and cold spots appear to be aligned along the same cosmic axis. The statistical significance of this alignment is low enough that it could, in theory, be a fluke, but it is persistent and unnerving. What could possibly cause such a large-scale asymmetry? One possibility is that we are being fooled by something much closer to home. Perhaps the glow of dust within our own Milky Way galaxy, or the magnetic fields of the solar system, are contaminating the signal, imprinting a local signature onto the primordial map. Teams have worked tirelessly to subtract these foregrounds, but the anomaly stubbornly remains. If it is not a local effect, the implications are staggering. It could be a relic from the era before cosmic inflation, a fingerprint of the universe's initial conditions that the rapid expansion failed to erase completely. Some theorists propose it points to a finite universe with a complex topology, where space is connected in a way that creates observable patterns. Others wonder if it is evidence of a primordial magnetic field that stretched across the entire cosmos, tugging at the infant plasma. Could this axis be a window into a time before the Big Bang, a scar from a previous cosmic cycle? The very idea forces us to reconsider the universe's most basic symmetry. As we confront this potential crack in the cosmological principle, our search for understanding leads us from the vast expanse of the early universe to the bizarre and counterintuitive world of the impossibly small. The unsettling alignment in the cosmic background radiation hints at a universe that is not as uniform as we believed, but this challenge to our cosmic principles pales in comparison to a fundamental paradox lurking in the void itself. According to our best theories, empty space is not empty at all. Quantum field theory tells us that the vacuum of space is a seething, bubbling sea of energy. At the tiniest scales, virtual particles constantly pop in and out of existence, borrowing energy from the vacuum for fleeting moments before annihilating each other. This activity gives every cubic centimeter of so-called nothingness a theoretical energy density of staggering proportions. When physicists calculate the cumulative effect of all these quantum fluctuations, they arrive at a number for the vacuum energy that is absurdly large. This energy should act as a cosmological constant, a repulsive force driving the expansion of the universe. The problem is the calculated value is 120 orders of magnitude greater than the value we actually observe. 120 orders of magnitude is a 1 followed by 120 zeros. It is the worst mismatch between theory and observation in the entire history of science. Nobel laureate Steven Weinberg called it a clear failure of our current understanding, a catastrophe for theoretical physics. This is the vacuum catastrophe. If the quantum field theorists were right, the immense energy of the vacuum would have generated a repulsive force so powerful that the universe would have ripped itself apart moments after the Big Bang. Galaxies, stars, and life could never have formed. The fact that we are here to ponder the question means the observed cosmological constant is not just a little small, it is almost exactly zero. How can the theoretical energy of nothing be so immense, while the measured energy of nothing is so perfectly, life-permittingly tiny? This is the cosmological constant problem. One proposed solution involves a theoretical symmetry called supersymmetry. This idea posits that every known particle has a super-partner particle. The contributions of these partner particles to the vacuum energy could perfectly cancel out the contributions of the ordinary particles, bringing the net result close to zero. The catch is that if supersymmetry exists, it must be a broken symmetry because we do not see these super-partners in our particle colliders. This breaking would likely spoil the perfect cancellation, leaving us with a large value again. Another, more philosophical approach is the anthropic principle. This suggests that the cosmological constant has a range of possible values across a vast multiverse, and we simply find ourselves in one of the rare universes where the value is small enough to allow for the formation of galaxies and life. While this explains the observation, it does not provide a fundamental physical mechanism for why the constant is so small. We can even witness the reality of these quantum fluctuations in the laboratory through the Casimir Effect. Place two perfectly smooth, uncharged metal plates extremely close together in a vacuum. The plates act like walls, restricting the kinds of virtual particles that can pop into existence in the gap between them. Outside the plates, a wider variety of fluctuations can occur. This difference in quantum activity outside and inside the gap creates a subtle pressure that pushes the plates together. This tiny, measurable force is a direct, experimental signature that the vacuum is indeed alive with transient energy. Yet this experimental proof only deepens the mystery, because the energy we measure in the Casimir effect is still infinitesimally small compared to the theoretical prediction. How can nothingness be so full of theoretical power while exhibiting such profound observational silence? This vacuum catastrophe represents a fundamental schism between the world of the very small, governed by quantum mechanics, and the world of the very large, described by general relativity. Resolving it may require a theory that unifies them both, a theory that can finally tell us what nothing really is. This profound puzzle of empty space finds a strange parallel in the peculiar, almost lazy motion of certain stars that seem to defy the relentless pull of gravity. The silent rebellion of the vacuum is mirrored in the serene, orderly spin of distant galaxies, but this cosmic dance holds a secret that shattered our understanding of gravity. Spiral galaxies like our own Milky Way should rotate according to a simple rule, one that governs our solar system. The Sun's powerful gravity keeps the inner planets, like Mercury, whipping around at high speed, while the outer planets, like Neptune, plod along in a slow, stately orbit. This is Kepler's law in action, where orbital speed should fall off predictably with distance from the center. Yet when astronomers like Vera Rubin and Kent Ford began meticulously measuring the velocities of stars in other galaxies in the 1970s, they found something astonishing. Stars at the very edge of a galactic disk, far from the bright central bulge, were racing around just as fast as those snug near the core. The rotation curve, a graph of orbital speed versus distance, did not fall away. It stayed flat, a stubborn horizontal line that defied all expectations based on the glow of visible stars and gas alone. Vera Rubin recalled the data was so clear, the implication so inescapable that it left no doubt. The galaxies were enveloped in a massive, invisible halo of something that provided the extra gravitational glue. This was one of the most powerful pieces of evidence for dark matter. To map these curves, astronomers don't just look at stars. They use radio telescopes to track clouds of neutral hydrogen gas, known as HI. These vast, cold clouds extend far beyond a galaxy's visible starlight, tracing the gravitational pull into the deep darkness. The gas clouds, like the stars, also move far too quickly, confirming the flat rotation profile from the inner disk to the outermost, faintest reaches. This anomaly is not unique to giant spirals. Dwarf galaxies with far fewer stars show the same dramatic discrepancy, their tiny visible masses unable to hold onto gas that moves at such high speeds. A prime example is our neighbor, the Andromeda Galaxy. Precise tracking of individual stars and hydrogen clouds has created a detailed rotation curve that leaves no room for doubt. The amount of gravity required to produce the observed speeds is many times greater than the total mass of all its stars, gas, and dust. This missing mass problem sparked a fierce debate that continues today. Is the universe filled with a new kind of particle that we have yet to detect, or are we witnessing a fundamental flaw in our law of gravity? The dominant solution is dark matter, a cosmic scaffolding of cold, slow-moving particles that clumps around galaxies. Yet a vocal minority of physicists like Stacy McGaugh champion an alternative modified Newtonian dynamics, or MUND. This theory proposes that gravity behaves differently at extremely low accelerations, like those experienced in the outskirts of galaxies. It suggests that Newton's laws need a tweak. and that what we perceive as dark matter is really just gravity working in a way we never before anticipated. Intriguingly, one can predict the rotation curves of many galaxies from their visible matter alone, a surprising success, but it struggles to explain all the evidence, particularly the gravitational lensing seen in colossal galaxy clusters or the precise patterns in the cosmic microwave background. The debate forces us to ask a profound question. Is the universe mostly made of something we cannot see, or are we still, after centuries, misunderstanding the fundamental force that holds it all together? This galactic puzzle finds a strange, miniature counterpart in the heart of our own solar system, where a different kind of drift continues to baffle our best instruments. That same primordial light, the cosmic microwave background, holds a chilling secret in the constellation Eridanus. Stretching across a vast region of sky, there exists a cold spot so immense and so profound it defies easy explanation. This is not a simple statistical blip, but a colossal patch of the universe that is significantly colder than the surrounding afterglow, a cosmic chill spanning over 1 billion light-years. When scientists first spotted it in data from the Wilkinson microwave anisotropy probe, they were stunned. Its size and temperature deviation were far larger than standard models of cosmic inflation predicted for a random fluctuation. The chance of such a feature appearing naturally in our universe was estimated to be less than 2%, a figure that demands attention. The European Space Agency's Planck satellite later confirmed its existence with even greater precision, cementing its status as a genuine cosmological anomaly. The simplest explanation is a supervoid, a staggering underdensity in the cosmic web. In such a region, the concentration of galaxies and dark matter would be unusually sparse. As light from the cosmic microwave background travels through a void, it must climb out of the gravitational well created by the missing mass. This journey saps its energy, causing a slight redshift and making the light appear colder to our telescopes, an effect known as the integrated Sachs-Wolf effect. Scientists have indeed found a large underdensity in the Eridanus constellation, but here lies the core of the mystery. The discovered supervoid, while enormous, does not seem nearly large or empty enough to account for the extreme coldness of the spot. The numbers simply do not add up, leaving a significant portion of the cooling unexplained by known physics. This gap has led to more exotic proposals. Could the cold spot be a cosmic texture, a hypothetical defect in the fabric of space-time left over from the universe's earliest, most violent moments? The unraveling of such a knot could release energy that imprints a cold signature on the background radiation. An even more profound idea comes from cosmologist Laura Mersini-Horton, who suggests it could be a bruise, the observable evidence of a collision between our universe and another bubble universe in the vast multiverse. In this scenario, the cold spot is a direct window into a reality beyond our own. The Dark Energy Survey has meticulously mapped the galaxy distribution in this region, seeking to definitively measure the true scale of any associated void. While their work has refined our understanding, the fundamental mismatch between the observed cold and the observed emptiness persists. This lingering cosmic chill forces us to confront a radical possibility. Are we seeing the first observational hint of a multiverse, a shadow cast by a neighboring cosmos we can never directly visit? The implications are as profound as they are humbling, suggesting our entire reality might be just one island in an infinite archipelago of universes. From the profound chill of a cosmic void, we turn to particles of almost unimaginable violence. Streaking through the void are atomic nuclei carrying more energy than a professionally thrown fastball, all compressed into a single subatomic projectile. These are ultra-high-energy cosmic rays, and they possess millions of times the power achievable in our largest particle colliders. Their existence alone is a cosmic affront, a direct challenge to the known laws of physics. The most extreme example ever recorded is nicknamed the "Oh my God" particle. Detected in 1991, it was likely a single proton traveling at a staggering 99.9999999999996% of the speed of light. The energy packed into that one tiny speck was equivalent to a bowling ball dropped from waist height, a phenomenal concentration of force from a natural particle accelerator we cannot yet locate. Physicist James Cronin, a Nobel laureate who helped pioneer their study, stated that their very detection forces us to rethink our models of the most powerful astrophysical engines. The mystery is compounded by their rarity. Catching them requires enormous, patient observatories like the Pierre Auger Observatory in Argentina, which uses an array of 1,600 water tanks spread over an area the size of Rhode Island. These tanks do not see the primary particle itself. Instead, they detect the cascading avalanche of secondary particles created when the cosmic ray slams into the upper atmosphere, a phenomenon known as an extensive air shower. By studying the footprint of this shower, scientists can work backwards to calculate the original particle's energy and direction. Yet, tracing them back to their source is like trying to follow the path of a bullet bent by 100 powerful magnets. Galactic and intergalactic magnetic fields twist the trajectories of these charged particles, scrambling their paths and obscuring their points of origin. This deflection creates a fundamental fog, making it nearly impossible to point to a single object in the sky and declare it the culprit. The greatest theoretical puzzle is the GZK Cutoff, named for physicists Greisen, Zatsepin, and Kuzmin. This is a predicted energy limit. Cosmic rays with energies above this threshold should not be able to travel great distances across the universe. They should constantly collide with the photons of the cosmic microwave background, the leftover heat from the Big Bang. In these collisions, they would lose energy, rapidly bleeding their immense power until they fall below the cutoff. The fact that we observe particles like the "Oh my God" particle, with energies far exceeding this limit, means one of two things. Either their sources are incredibly close to us in cosmic terms, within our local supercluster of galaxies, or our understanding of how particles interact at these extreme energies is fundamentally wrong. So, what cosmic objects could possibly be these nearby accelerators? The list of suspects is a catalogue of celestial violence, active galactic nuclei, where matter spirals into supermassive black holes, can generate colossal jets of plasma. Gamma-ray bursts, the most energetic explosion since the Big Bang, are another prime candidate. The mergers of neutron stars, which shake the fabric of space-time itself, are also thought to be capable of such acceleration. Some data has shown a tantalizing correlation between the arrival directions of the highest energy cosmic rays and starburst galaxies, which are undergoing frenzied periods of star formation and resulting supernova explosions. These environments are chaotic and powerful, but whether they can produce the absolute peak energies we see remains an open question. There are even more exotic proposals, such as the decay or annihilation of super-heavy dark matter particles lurking in the halo of our own Milky Way. This would provide a local source, neatly sidestepping the GZK cutoff problem. What natural process can focus energy with such terrifying precision, hurling a single particle across the universe with the force of a macroscopic object? Each one that strikes our atmosphere is a messenger from the most extreme environments in existence, carrying secrets we are only just beginning to decode. The sheer violence of cosmic rays finds a strange counterpoint in the subtle, irregular flickering of a single, unassuming star. KIC 8462852, known as Boyajian star, behaves like no other. Its light does not dip in the predictable, rhythmic way of a planet passing in front of it. Instead, it plunges into darkness without warning, sometimes dimming by up to 22%, a staggering amount that would require an object half the width of the star itself. This is not a single transit, but a chaotic series of deep, asymmetrical dips that last for days or weeks, a pattern that defies any conventional explanation. Citizen scientists from the Planet Hunters project were the first to flag this bizarre light curve in data from NASA's Kepler telescope, spotting a pattern so strange that professional astronomer Tabitha Boyajian, after whom the star is now popularly named, initially called it the most mysterious star in the galaxy. The dips are far too deep and irregular to be caused by a planet, and the star itself is a mature F-type star, not given to such wild, youthful outbursts. The mystery captured the public imagination with one tantalizing, though highly speculative, hypothesis suggesting a swarm of alien megastructures, like a vast array of energy-collecting panels, could be orbiting the star and blocking its light. Astronomer Jason Wright helped popularize this idea, though he stressed it was a last resort, only after all natural explanations had been exhausted. The scientific community mobilized, training radio telescopes on the star to listen for any artificial signals and studying its light with powerful spectrographs. These spectroscopic observations were crucial as they revealed that the dimming was wavelength dependent. The star dimmed more in blue light than in red light. This was a critical clue, pointing strongly toward the blocking material being composed of fine dust, which scatters blue light more effectively rather than being solid, opaque objects. This finding largely ruled out the monolithic megastructure idea, but it only deepened the natural mystery. What could produce such immense, clumpy, and dynamic clouds of dust? One leading theory proposes a fragmented comet swarm, perhaps torn apart by the star's gravity, creating a vast, irregular cloud of debris. Another suggests a recent planetary collision, littering the orbit with pulverized rock and dust. Some have even pondered whether we are seeing the remnant debris of a forming planet, a protoplanetary disk in its final, chaotic stages. Yet Boyajian star is not entirely alone. Another star, Epoch 204278916, also exhibits extreme, irregular dimming, though its dips have been linked to a warped inner disk of dust. This suggests that while rare, such phenomena might be part of a new class of stellar behavior we are only beginning to recognize. Follow-up observations from the Transiting Exoplanet Survey Satellite, or TESS, have continued to monitor the star, capturing new dimming events in real time. Each new dip provides more data, but a definitive answer remains elusive. The dust is clearly present, but its origin and the reason for its chaotic, clumpy distribution are still unknown. How does a star create or acquire a circumstellar environment of such profound and unpredictable complexity? This stellar oddity, a single point of light behaving against all expectations, forces us to acknowledge that even the most common objects in the cosmos can harbor profound secrets. A river of galaxies is flowing through the cosmos, and our Milky Way is caught in its current. This is the mystery of the Great Attractor, a colossal gravitational anchor in the depths of intergalactic space that is pulling our galaxy, along with thousands of others, toward an unseen point. For decades, this anomaly was hidden from our view, lying directly behind the dusty plain of our own Milky Way in a region astronomers call the Zone of Avoidance. The first hints emerged in the 1970s, when mapping the motions of nearby galaxies revealed peculiar velocities, movements that could not be explained by the overall expansion of the universe alone. Something immense was tugging on us, Astronomer Alan Dressler described this collective motion as a silent river, a vast flow of galaxies toward a gravitational Great Valley. The sheer scale of this pull suggests a concentration of mass so tremendous it challenges our existing maps of the universe's large-scale structure. To peer through the obscuring dust of the zone of avoidance, scientists turn to eyes that see in different light. Infrared telescopes like those on the Spitzer Space Telescope can penetrate the cosmic dust, revealing the faint glow of stars and galaxies hidden behind the Milky Way's bulge. These surveys confirmed the presence of a massive overdensity, now identified as part of the even larger Laniakea supercluster, our cosmic home of 100,000 galaxies. At the heart of the Great Attractor's pull lies the Norma cluster, a dense knot of galaxies and hot gas, but even its considerable mass is not enough to account for the entire observed flow. This points to an even larger source of gravity lurking beyond, the Shapley supercluster, the most massive known structure in our local universe, which lies farther along the same direction and adds its own immense pull to the cosmic current. The true nature of this gravitational sink is being refined by precise data from missions like Gaia, which meticulously tracks the motions of stars within our own galaxy. By subtracting the Sun's orbit around the galactic center, Gaia helps pin down the Milky Way's true trajectory through intergalactic space, offering a clearer picture of the forces acting upon us. A powerful illustrative example comes from radio astronomy. Projects using telescopes like the Future Square Kilometre Array, or SCAR, will map the distribution of neutral hydrogen gas in millions of galaxies. Since this gas is unaffected by dust, it provides a pristine view of galaxy motions, allowing scientists to create a three-dimensional velocity map of the entire region and trace the gravitational field back to its source. This vast, invisible architecture is shaped overwhelmingly by dark matter, whose gravitational potential wells guide the flow of galaxies like water down a mountainside. What truly lies at the core of this cosmic confluence? Is it simply the combined gravity of known superclusters, or could there be something even more exotic, a flaw in the fabric of space-time or a concentration of mass that redefines our understanding of cosmic structure? The Great Attractor reminds us that we are not still observers, but passengers on a galactic ship sailing toward an unseen horizon. This immense gravitational puzzle finds a strange counterpart in the bizarre and counterintuitive rules that govern the smallest particles in existence. Even Albert Einstein was deeply unsettled by the implications of quantum entanglement, famously dismissing it as spooky action at a distance. This phenomenon begins with a seemingly simple idea that two particles can be born together, their fates forever linked. Once entangled, the particles enter a shared state of superposition, meaning their properties, like spin or polarization, are not fixed until the moment one is measured. The instant you measure one particle and force its property to take a definite value, its partner, no matter how far away, instantly assumes a corresponding value. This connection appears to happen faster than light, challenging the cosmic speed limit set by Einstein's own theory of relativity. This was the heart of the EPR paradox, a thought experiment conceived by Einstein, Podolsky, and Rosen in 1935 to argue that quantum mechanics must be incomplete. They believed a deeper, hidden layer of reality must exist where particles carried definite properties from the start, an idea known as local realism. For decades, this remained a philosophical debate. Then, physicist John Bell devised a mathematical theorem in the 1960s that could test whether local hidden variables could explain the weird correlations. He showed that if quantum mechanics was correct, the results of certain entangled particle measurements would violate a specific inequality. The baton was passed to experimenters like Alain Aspect, who in the 1980s performed a series of elegant tests with entangled photons. His results were clear and decisive. They violated Bell's inequality. The particles were correlated in ways that no local, hidden variable theory could possibly explain. The spooky action was real. To understand why this is so strange, think of a pair of magical gloves. If you could entangle them and then mail one to a friend on the other side of the galaxy, the moment your friend opens the box and sees a left-handed glove, you would instantly know yours is the right-handed one. The bizarre quantum truth is that neither glove was left or right until the very moment one was observed. The act of looking itself seems to crystallize reality out of a cloud of possibility. This leads to the profound question of what measurement actually is, and how the definite world we experience emerges from fuzzy quantum probabilities. This process of a quantum system losing its coherence and interacting with the environment is called decoherence, and it is one of the biggest hurdles in building quantum computers. These machines rely on maintaining entanglement between many quantum bits or qubits to perform calculations that are impossible for classical computers. A qubit can be a 1, a 0, or both at the same time thanks to superposition. Harnessing entanglement allows these computers to explore countless solutions simultaneously. But decoherence constantly threatens to collapse these delicate states, making the engineering a monumental challenge. Over the years, scientists have closed every potential loophole in these entanglement experiments. They have separated particles by hundreds of miles using fiber optic cables and even satellites to ensure no hidden signal could travel between them. In 2015, a landmark loophole-free Bell test was declared, using entangled electrons separated by over a kilometer. The results were unequivocal. The universe is genuinely non-local at the quantum level. So how do we reconcile this with relativity? The prevailing view is that while the correlation is instantaneous, no usable information is actually transmitted faster than light. You cannot use entanglement to send a message because the outcome on your end is always random. You only know what your partner got after you compare notes through a classical, slower-than-light channel. This has forced physicists to reconsider the very nature of reality. Perhaps particles are not separate entities but connected through a deeper level of physics, as suggested by the holographic principle. Or maybe every possible measurement outcome actually occurs in a branching multiverse, as the many worlds interpretation suggests. How does this spooky, interconnected quantum layer beneath our classical reality influence the fundamental constants that shape our cosmos? The spooky interconnectedness of quantum particles suggests a universe built on delicate relationships. But what if the very constants governing those relationships are not constant at all? Deep within the light of ancient quasars, astronomers may have found evidence that a fundamental number in physics is changing. This is the fine structure constant, denoted by the Greek letter alpha. It is a pure number that governs the strength of the electromagnetic force, controlling how light interacts with matter, how atoms hold together, and the very nature of chemistry itself. For decades, we have assumed alpha was a fixed pillar of reality, unchanging across space and time. The work of astronomer John Webb and his team has thrown that assumption into doubt. By analyzing the absorption lines in the spectra of incredibly distant quasars, they have detected tiny but statistically significant variations in alpha. The light from these quasars has traveled for billions of years, and as it passes through intergalactic gas clouds, specific elements like iron, magnesium, and silicon imprint a unique fingerprint of dark lines on the spectrum. The precise spacing of these lines depends critically on the value of alpha at the time the light was absorbed. When Webb's team measured these spacings, they found that billions of years ago, in certain directions of the sky, alpha was slightly smaller than it is today. In other directions, it appeared slightly larger. This was not a uniform change, but a potential dipole, a directional variation across the cosmos, as if the universe has a preferred axis where the laws of physics are subtly different. This single finding, if confirmed, would force us to rewrite the standard model of particle physics and challenge Einstein's equivalence principle, a cornerstone of general relativity which assumes the laws of physics are the same everywhere. To understand the staggering precision involved, consider the analysis of a quasar like Euler's J1120 plus 0641, whose light has journeyed for over 13 billion years. Scientists use powerful spectrographs on telescopes like the Very Large Telescope in Chile to spread the quasar's faint light into a rainbow of incredible detail. They then search for the specific patterns of missing light caused by these ancient gas clouds. Any minuscule shift in the expected positions of these lines, smaller than the width of a single pixel on the detector, could indicate a change in alpha. The implications are profound. A varying constant could be a signature of extra dimensions of space, as predicted by string theory. In such models, what we perceive as constants are actually the sizes and shapes of these hidden dimensions, and if those dimensions evolve, our constants would evolve with them. Alternatively, it could mean that the speed of light itself is not a constant, but has changed over the life of the universe. Scientists have sought to test this using earthly laboratories. The Oklo Natural Nuclear Reactor in Gabon, Africa, is a fascinating check. 2 billion years ago, a rich vein of uranium ore sustained a natural, self-regulating nuclear fission reaction. The nuclear processes that occurred then were sensitive to the value of alpha. By analyzing the remnant isotopes left behind, physicists can work backwards to determine the fine structure constant at that time. The results from Oklo are tantalizingly inconclusive, but generally consistent with no change, creating a puzzle when contrasted with the quasar data. In modern labs, researchers use atomic clocks to test for any current drift in alpha. These clocks, the most precise timekeeping devices ever built, rely on the immutable vibration frequencies of atoms. By comparing two different types of atomic clocks over many years, scientists can see if their relative ticking rates drift, which would indicate a changing constant. So far, these exquisitely sensitive experiments have found no evidence of change in our local environment, deepening the mystery of the quasar results. Could it be that the laws of physics are not a universal symphony, but a local dialect that changes from one galactic neighborhood to another? The quest to understand these potential cracks in reality's foundation pushes our instruments to their absolute limits, searching for a whisper of new physics in the oldest light we can see. Our universe's first few minutes were a frenetic forge, creating the primordial elements that would seed everything to come. Yet one of its predicted products is stubbornly missing. According to the precise calculations of Big Bang nucleosynthesis, the infant cosmos should have manufactured a specific amount of a light element known as lithium-7. The theory is a masterpiece of modern cosmology, accurately predicting the observed abundances of hydrogen and helium, but when it comes to lithium, the numbers fail. The universe holds only about 1/3 of the lithium that our models insist should be there. This is the cosmological lithium problem, a persistent deficit that cosmologist Brian Fields describes as a clear signal that something is missing from our picture of the universe's first nuclear furnace. The predictions come from sophisticated computer codes that model the nuclear reactions in the first 20 minutes after the Big Bang. These models rely on key inputs like the density of ordinary matter, which has been measured with breathtaking accuracy by the Planck satellite through the cosmic microwave background. When you plug Planck's numbers into the Big Bang nucleosynthesis code, the lithium discrepancy does not vanish, it sharpens. The theory and the observation are in direct, uncomfortable conflict. So where did the lithium go, or was it never made in the expected amounts to begin with? One possibility is that our understanding of the nuclear physics itself is incomplete. The key reaction rates involved in creating and destroying lithium are extraordinarily difficult to measure in laboratories because they occur at such low energies. Deep underground in Italy, the lunar experiment uses a particle accelerator shielded by rock to recreate the conditions of the early universe, probing these subtle nuclear interactions with unprecedented precision. They are searching for a hidden nuclear pathway that could have destroyed lithium as fast as it formed. Another line of investigation looks to the oldest stars in our galaxy. These ancient, metal-poor stars are thought to be time capsules, preserving the chemical imprint of the early universe in their atmospheres. Astronomers carefully measure the spectral signature of lithium in these halo stars, and the result is always the same. The lithium abundance is consistently lower than the Big Bang prediction. This is not a case of a few odd stars. It is a universal trend among the most pristine objects we can find. Some have suggested that these stars themselves are the culprits, slowly destroying lithium over billions of years in their own nuclear furnaces. But detailed stellar models struggle to explain the uniform nature of the deficit across so many different types of old stars. The search for a pure, unaltered sample has led astronomers to hunt for the mythical population 3 stars, the very first generation of stars born from nothing but primordial gas. If we could find one, its lithium content would be the ultimate test. Yet these first stars have never been conclusively observed and may have all died in spectacular supernova long ago. More exotic solutions are also on the table. Perhaps unknown particles, like certain types of dark matter, were present in the early universe and decayed, altering the nuclear reactions during those critical first minutes. Or maybe the fine structure constant, which governs the strength of nuclear forces, was slightly different during the era of nucleosynthesis. How can a theory as successful as the Big Bang leave such a clear and elemental signature unaccounted for? This missing lithium is a tiny but persistent crack in the foundation of our cosmic origin story, a reminder that the recipe for our universe may still have a few secret ingredients. From this elemental puzzle in the first moments of time, we turn to the grandest structures the universe has ever built. That missing lithium from the Big Bang is just one piece of a larger cosmic inventory problem. Our most trusted models give us a precise ledger for all the ordinary matter, the baryons that make up every star, planet, and gas cloud that we can see. Yet when astronomers add up all this visible material in the modern universe, they come up short by a staggering amount. Nearly half of all the ordinary matter predicted to exist is simply missing. This is the missing baryon problem, a quiet crisis that challenges our most basic ability to map the contents of the cosmos. We know the matter was created in the Big Bang, and we can see its imprint in the cosmic microwave background. But today, a huge portion of it has vanished from our view. The leading suspect for this hidden reservoir is the warm-hot intergalactic medium, a vast web of diffuse, superheated gas that fills the space between galaxies. This gas is so hot it emits only faint X-rays, and so diffuse it is virtually transparent, making it the perfect cosmic hiding place. Astronomer Fabrizio Nicastro and his team have spent years hunting for this ghostly material. Using the Chandra X-ray Observatory, they pointed the telescope at a distant quasar, using its brilliant light as a cosmic flashlight. As this light traveled across billions of light years, it passed through the filaments of the cosmic web. The team detected specific dips in the quasar's X-ray spectrum, the telltale absorption signature of highly ionized oxygen atoms. They were seeing the fingerprints of the missing baryons, caught in the act of hiding within these immense, wispy tendrils of gas. This discovery was a major breakthrough, but it only confirmed a small portion of the total missing mass. To complete the cosmic inventory, scientists use a variety of methods. They study the Lyman alpha forest, the complex array of absorption lines seen in the ultraviolet spectra of quasars, which maps the distribution of neutral hydrogen gas throughout the universe. They also use the cosmic microwave background as a baseline, comparing the amount of matter present in the infant universe to what we see today. The discrepancy points to a dramatic story of cosmic evolution. Powerful forces are at work, ejecting matter from galaxies on a colossal scale. Supernova explosions and intense radiation from black holes generate galactic winds, which can blow enormous fountains of gas out of a galaxy and into the intergalactic void. This feedback process is crucial for regulating star formation, but it also scatters a significant fraction of a galaxy's baryons into the deep darkness, where they become incredibly difficult to track. The warm-hot intergalactic medium is not a uniform blanket, but a complex structure with a wide range of temperatures and densities. Detecting it requires probing specific energy levels. This is where fast radio bursts become a revolutionary tool. As these brief, powerful signals travel across the universe, their waves are dispersed by the free electrons they encounter in this tenuous gas. By measuring the precise dispersion of a burst, astronomers can count the total number of electrons along its path, providing a direct measure of the baryonic matter it has traveled through. Future missions are being designed specifically for this hunt. The Athena Space Telescope, planned by the European Space Agency, will have the sensitivity to survey large areas of the sky in X-rays, finally mapping the structure and properties of this hidden cosmic ocean. So where is all the ordinary matter hiding? It is all around us, woven into a thin, hot fog that permeates the vast spaces between the islands of galaxies. Finding it not only balances the cosmic books, but reveals the violent processes that have shaped galaxies from their birth. This grand struggle to account for the universe's contents forces us to confront an even more fundamental question, one about the very nature of space and time. Even the majestic whirlpools of spiral galaxies and the smooth orbs of ellipticals cannot capture the full story of cosmic structure. Scattered across the sky are galactic misfits, bizarre formations that defy the neat categories of the Hubble sequence. These peculiar galaxies, with their polar rings, vast empty hoops, and distorted shapes, are not mere curiosities. They are cosmic experiments revealing the violent and creative processes that build galactic empires. Astronomer Alar Tuma's pioneering simulations demonstrated how the gentle dance of gravity can become a sculptor of chaos. When two galaxies pass too close, their mutual gravitational pull does not simply merge them instantly. Instead, they stretch out vast tidal tails of stars and gas, creating bridges and shells of material that can persist for billions of years, a permanent record of a catastrophic encounter. Consider the Cartwheel Galaxy, a stunning bullseye in the depths of space. Its perfect ring is the aftermath of a cosmic puncture, a smaller galaxy that shot straight through its heart. The impact sent a colossal wave of star formation rushing outward, like a ripple across a pond, leaving a brilliant blue ring of newborn stars in its wake. Then there is Hoag's object, an even profound riddle. Here, a nearly perfect ring of young, blue stars encircles an ancient yellow core with a seemingly empty black gap between them. There is no visible remnant of a collision, no second galaxy that could have caused this. Its formation remains one of astronomy's most beautiful and enduring puzzles. Did a smaller galaxy get entirely swallowed, leaving only this ring as its ghost, or is this the result of a rare, stable resonance within a disk of gas? The answers are written in the light of these stellar anomalies. With the James Webb Space Telescope, we are now witnessing these chaotic processes at the dawn of time. In the early universe, galaxy mergers were the rule, not the exception. JWST infrared eyes see high redshift galaxies that are shockingly disordered, a zoo of odd shapes and clumpy structures that are actively building themselves through frantic collisions and gas accretion. These ancient misfits are the building blocks of the majestic spirals we see today. Among the modern oddities, the ultra-diffuse galaxies present a different kind of challenge. These faint, ghostly galaxies, like Dragonfly 44, have the spatial extent of the Milky Way but contain almost no stars. The real shock came when astronomers measured their motions and found they possessed very little dark matter, directly contradicting the standard model that says all galaxies are born within massive halos of this invisible substance. How did these galaxies form without dark matter's gravitational anchor? Could they be the mangled remnants of a larger galaxy, stripped bare in a past encounter? Each peculiar galaxy, from the ringed to the diffuse, forces us to acknowledge that galaxy evolution is not a single, monolithic story, but a complex tapestry woven from gravity, collisions, and the mysterious hand of dark matter. What do these galactic misfits teach us? They reveal a universe that thrives on creative destruction, where the standard rules are constantly being bent and rewritten. This grand diversity of cosmic structures hints at a deeper layer of strangeness, one that may not be confined to the vastness of space, but to the very flow of time itself. Gamma-ray bursts flash with the raw power of a billion suns, yet their light carries a subtle distortion that might rewrite our understanding of time itself. According to Einstein's relativity, the expansion of the universe should stretch the light from these colossal explosions, making their high-energy signals appear to arrive just a fraction slower than their lower-energy counterparts. This is a cosmic time dilation effect, a predictable delay known as spectral lag. But for some bursts, the lag is all wrong. It is either too large, too small, or simply does not correlate with the burst's distance in a way that our models can explain. This anomaly in the very heartbeat of a gamma-ray burst suggests that something fundamental is missing from our relativistic playbook. Astrophysicist Bing Zhang has meticulously analyzed how these temporal discrepancies relate to other burst properties, proposing that they could be a unique probe of space-time's underlying structure. The standard model for these events is the fireball model, where a cataclysm like a collapsing star or merging neutron stars launches a jet of plasma moving at nearly the speed of light. The incredible speed, described by a Lorentz factor, bunches the emitted radiation and should create a specific, smooth pattern of time delays between different energy photons. When the observed lags deviate from this pattern, it points to physics beyond the standard model. Satellites like Swift and Fermi are our watchmen for these cosmic bombs. Their precise instruments capture the entire light curve of a burst, from the initial brilliant flash to the fading afterglow, allowing scientists to dissect the arrival time of every photon. The correlation between a burst's redshift, which measures its cosmological distance, and its spectral lag is a key test. For the most distant bursts, we expect a longer lag due to the universe's expansion. The fact that this relationship often breaks down is deeply puzzling. One of the most telling cases was the short burst GRB 090510. Detected by the Fermi satellite, this burst originated from a neutron star merger, and showed an almost negligible spectral lag despite its considerable distance. Its incredibly brief and energetic pulses were used to place stringent limits on theories of quantum gravity. Some models suggest that space-time is not perfectly smooth, but has a minuscule, granular structure at the Planck scale. This quantum foam could cause high-energy photons to travel at very slightly different speeds, an effect that would accumulate over billions of light-years. GRB 090510's sharp pulses showed no such dispersion, ruling out certain versions of these theories. Other explanations for the anomalous lags point to the emission mechanism itself. Perhaps the internal shocks within the jet are more complex than we thought, or magnetic fields play a greater role in sorting the energies of the emitted photons. More radical ideas involve a variable speed of light in the early universe or the influence of hidden extra dimensions subtly altering how light propagates. Could these fleeting flashes from the edge of time be illuminating the granular texture of reality? Each anomalous lag is a potential fingerprint of quantum gravity, a signal from a realm where space and time themselves break down into something entirely new. As we explore time's strange behavior in these violent endings, another anomaly calls to us from the very beginning of everything. The universe was once a cosmic fog, a vast sea of neutral hydrogen that blocked the passage of light. Then, over hundreds of millions of years, a great clearing began. This was the Epoch of Reionization, the moment the cosmos turned on its lights, and it remains one of our most profound puzzles. The process seems straightforward enough. The first stars and galaxies switched on, their intense ultraviolet radiation tearing electrons away from hydrogen atoms, transforming the opaque fog into a transparent universe. Yet the precise timing and the primary sources of this cosmic dawn are deeply uncertain, challenging our entire narrative of how structure emerged from the primordial dark. Astronomer Richard Ellis has long championed the idea that countless faint, early galaxies provided the flood of ionizing photons needed for this task. But when we count the galaxies we can see, their collective output falls dramatically short of the energy required to complete reionization by the time we know it ended. It is as if we have found only a few small campfires when the evidence points to a continent-spanning wildfire. We probe this ancient transition in two primary ways. The first is through the cosmic microwave background. The Planck satellite's measurement of the CMB's polarization provides a key number called the optical depth. This value tells us how much the CMB photons were scattered by free electrons during reionization, and it implies the process was already underway when the universe was only around 400 million years old. This early start is difficult to reconcile with models that rely solely on the first generation of stars. The second probe is the Lyman alpha forest, the intricate web of absorption lines seen in the spectra of even more distant quasars. These lines are the shadows cast by the last remaining patches of neutral hydrogen, allowing us to map the final stages of the clearing. The data suggests reionization was not a smooth, uniform process, but a patchy and complex one, with some regions becoming transparent long before others. Could active galactic nuclei, the furious cores of galaxies with supermassive black holes, have provided an early, potent source of ionizing radiation? Their powerful beams could have carved out vast transparent bubbles in the neutral hydrogen, or are we underestimating the first galaxies themselves? The James Webb Space Telescope is now peering back to this critical era, and its findings are both thrilling and confounding. It has discovered galaxies at redshifts greater than 10, meaning they existed well before reionization was complete. Some of these early galaxies show signs of being prodigious producers of ultraviolet light, but a crucial piece of the puzzle is missing: the physics of the escape fraction. This is the percentage of ionizing radiation that actually escapes a galaxy's own gaseous halo to do its work on the intergalactic medium. If too much of this hard UV light is trapped by local gas and dust, the galaxy becomes a brilliant but isolated island, unable to contribute to the cosmic clearing. How did the universe's lights truly turn on? The answer seems to lie in a population of faint, numerous sources we have not yet fully seen, or in physical processes within early galaxies that we do not yet understand. This great reionization puzzle sets the stage for our final, and perhaps most unsettling, cosmic anomaly. The final cosmic anomaly strikes at the very heart of reality, questioning what happens to information when it crosses the point of no return. Stephen Hawking's revolutionary calculation showed that black holes are not truly black, but slowly evaporate by emitting a faint glow of particles, now known as Hawking radiation. This radiation, however, appears to be completely random, carrying no details about the matter that fell in. If a book were tossed into a black hole, Hawking's math suggested the hole would eventually vanish, leaving behind only thermal static, the information within the book seemingly erased from the universe forever. This creates a fundamental conflict, a direct violation of a core rule of quantum mechanics called unitarity, which states that information can never be truly destroyed. You could, in theory, run the universe's clock backwards and recover every detail of its past. The black hole information paradox pits Einstein's general relativity, which allows for information loss, against quantum theory, which forbids it. One of these foundational pillars of physics must break. Theorist Leonard Susskind championed the idea that information is not lost but somehow preserved. This led to the holographic principle, a breathtaking concept suggesting that all the information describing a three-dimensional volume of space, like the interior of a black hole, is actually encoded on its two-dimensional boundary, the event horizon. It is as if the universe operates like a cosmic hard drive, storing a perfect record of everything that falls in on the surface of the hole itself. The add S/CFT correspondence provides a precise mathematical framework for this, showing how a gravitational theory in one volume can be perfectly equivalent to a quantum theory on its boundary without gravity. The puzzle then becomes how this encoded information ever escapes. Recent breakthroughs in quantum gravity have centered on the Page curve, a graph devised by physicist Don Page. It describes how information, after being scrambled and hidden, begins to leak back out in the Hawking radiation as the black hole evaporates. Initially, the radiation is pure noise, but after the black hole has lost half its mass, the radiation starts to carry subtle correlations, effectively transmitting the hidden information back into the universe. The mechanism for this, however, remains deeply elusive. One radical proposal to resolve the paradox is the firewall hypothesis. It suggests that instead of a smooth, empty space at the event horizon, there exists a wall of blazing high-energy particles that would instantly incinerate anything crossing it. This violent boundary would prevent information from ever falling in, thus preserving it, but it shatters Einstein's principle of equivalence, the idea that an astronaut falling into a black hole would notice nothing special as they crossed the horizon. In laboratories here on Earth, scientists are testing these ideas using analog black holes. By creating sonic horizons in ultra-cold fluids known as Bose-Einstein condensates, where sound waves cannot escape a flowing drain, they can mimic the physics of event horizons and study the emission of Hawking-like radiation. While these experiments cannot prove what happens inside a real black hole, they provide a crucial testing ground for the quantum effects at play. How can the ultimate sinks of the cosmos possibly respect the delicate laws of quantum information? This final paradox weaves together every thread we have explored, from the spooky connections of quantum entanglement to the vast, hidden architecture of dark matter. Each anomaly, from the faint tug on a spacecraft to the evaporating whisper of a black hole, is a crack in our current understanding, a signpost pointing toward a deeper, more complete theory of reality. The cosmos is not a settled map, but a living frontier, and its greatest secrets are still waiting in the dark. We have traveled from the ghostly tug on distant probes to the evaporating secrets of black holes, a journey across 20 cosmic puzzles that each challenge our fundamental laws. These are not mere errors in our calculations, but profound invitations to explore a new frontier of physics, one that lies beyond the familiar realms of Einstein's relativity and quantum mechanics. Science does not advance by polishing what we already know, but by stumbling upon the inexplicable and having the courage to follow it into the dark. Carl Sagan beautifully captured this spirit when he said that somewhere, something incredible is waiting to be known. These anomalies are the beacons that guide us toward that incredible something. They are the questions that will shape the next century of discovery, potentially leading to technologies that harness the vacuum itself or grant us insights into a vast multiverse. I am curious to know which of these mysteries resonates most deeply with you. Was it the silent river of the great attractor, the spooky connection of quantum entanglement, or the stellar strangeness of Boyajian's star? Share your thoughts in the comments below, and if you want to continue this journey of questioning and wonder, subscribe for more explorations into the cosmos. Our greatest adventure is just beginning, and it is a story we are uncovering together.